Exact algebraic expressions for trigonometric values are sometimes useful, mainly for simplifying solutions into radical forms which allow further simplification. All trigonometric numbers, sines or cosines of rational multiples of 360 degrees, are algebraic numbers, but not all of these are expressible in terms of real radicals. When they are expressible more specifically in terms of square roots. All values of the sines, cosines, and tangents of angles at 3 degrees increments are derivable in radicals using identities: the half-angle identity, the double-angle identity, and the angle addition/subtraction identity, and using values for 0 degrees, 30 degrees, 36 degrees, and 45 degrees. Note that 1 degree equals pi, 180 radians. According to Niven's theorem, the only rational values of the sine function for which the argument is a rational number of degrees are 0, 1/2, 1, -1/2, and -1. According to Baker's theorem, if the value of a sine, a cosine or a tangent is algebraic, then either the angle is rational number of degrees, or the angle is a transcendental number of degrees. That is, if the angle is an algebraic, but non-rational, number of degrees, the trigonometric functions have a transcendental value. Scope of this article. The list in this article is incomplete in several senses. First, the trigonometric functions of all angles that are integer multiples of those given can also be expressed in radicals, but some are omitted here. Second, it is always possible to apply the half-angle formula to find an expression in radicals for a trigonometric function of 1/2 of any angle on the list, then half of that angle, etc. Third, expressions in real radicals exist for a trigonometric function of a rational multiple of pi if and only if the denominator of the fully reduced rational multiple is a power of 2 by itself, or the product of a power of 2 with the product of distinct Fermat primes, of which the known ones are 3, 5, 17, 257, and 65,537. This article only gives the cases based on the Fermat primes 3 and 5. Thus, for example, given in the article 17, gone, is not given here. Fourth, this article only deals with trigonometric function values when the expression in radicals is in real radicals, roots of real numbers. Many other trigonometric function values are expressible in, for example, cube roots of complex numbers that cannot be rewritten in terms of roots of real numbers. For example, the trigonometric function values of any angle that is 1/3 of an angle considered in this article can be expressed in cube roots and square roots by using the cubic equation formula to solve, but in general the solution for the cosine of the 1/3 angle involves the cube root of a complex number. In practice, all values of sines, cosines, and tangents not found in this article are approximated using the techniques described at generating trigonometric tables: table of some common angles, table of constants, values outside the 0 degrees, 45 degrees angle range are trivially derived from these values, using circle axis reflection symmetry. In the entries below, when a certain number of degrees is related to a regular polygon, the relation is that the number of degrees in each angle of the polygon is times the indicated number of degrees. This is because the sum of the angles of any n-gon is 180 degrees times, and so, the measure of each angle of any regular n-gon is 180 degrees times divided by n. Thus, for example, the entry 45 degrees square means that, with n equals 4, 180 degrees divided by n equals 45 degrees, and the number of degrees in each angle of a square is times 45 degrees equals 90 degrees. 0 degrees. Fundamental 1.5 degrees. Regular hecatonicosagon 1.875 degrees. Regular neocontahexagon 2.25 degrees. Regular octacontagon 2.8125 degrees. Regular hexacontatetragon 3 degrees. Regular hexacontagon 3.75 degrees. Regular tetracont-octagon 4.5 degrees. Regular tetracontagon 5.625 degrees. Regular triacontadigon 6 degrees. Regular triacontagon 7.5 degrees. Regular icosatetragon 9 degrees. Regular icosagon 11.25 degrees. Regular hexadecagon 12 degrees. Regular pentadecagon 15 degrees. Regular dodecagon 18 degrees. Regular decagon 21 degrees. Sum 9 degrees plus 12 degrees 22.5 degrees. Regular octagon 24 degrees. Sum 12 degrees plus 12 degrees 27 degrees. Sum 12 degrees plus 15 degrees 30 degrees. Regular hexagon 33 degrees. Sum 15 degrees plus 18 degrees 36 degrees. Regular pentagon, where is the golden ratio, 39 degrees. Sum 18 degrees plus 21 degrees 42 degrees. Sum 21 degrees plus 21 degrees 45 degrees. Square 54 degrees 60 degrees. Equilateral triangle 67.5 degrees 72 degrees 75 degrees 90 degrees. Fundamental calculated trigonometric values for sine and cosine. The trivial ones in degree format. 0, 30, 45, 60, and 90 can be calculated from their triangles, using the Pythagorean theorem. N times pi, geometrical method applying Ptolemy's theorem to the cyclic quadrilateral ABCD defined by 4 successive vertices of the pentagon. We can find that, which is the reciprocal one, phi of the golden ratio. CRD is the chord function, thus, but ax plus xc equals ac, so a plus a2, b equals b. Solving this gives a, b equals 1, phi, as above. Similarly, so algebraic method, the multiple angle formulas for functions of where and can be solved for the functions of. Since we know the function values of, the multiple angle formulas are, when or, we let or and solve for. One solution is 0, and the resulting fourth degree equation can be solved as a quadratic in, when or, we again let or and solve for, which factors into n times pi. 29 degrees is 45 minus 36, and 27 degrees is 45 minus 18, so we use the subtraction formulas for sine and cosine. N times pi. 36 degrees is 36 minus 30, 12 degrees is 30 minus 18, 24 degrees is 54 minus 30, and 42 degrees is 60 minus 18, so we use the subtraction formulas for sine and cosine. N times pi. 63 degrees is 18 minus 15, 21 degrees is 36 minus 15, 33 degrees is 18 plus 15, and 39 degrees is 54 minus 15, so we use the subtraction formulas for sine and cosine. Strategies for simplifying expressions. Rationalize the denominator. If the denominator is a square root, multiply the numerator and denominator by that radical. If the denominator is the sum or difference of two terms, multiply the numerator and denominator by the conjugate of the denominator. The conjugate is the identical, except the sign between the terms is changed. Sometimes you need to rationalize the denominator more than once. Split a fraction in two. Sometimes it helps to split the fraction into the sum of two fractions and then simplify both separately. Squaring and square rooting. If there is a complicated term, with only one kind of radical in a term, this plan may help. Square the term, combine like terms, and take the square root. This may leave a big radical with a smaller radical inside, but it is often better than the original. Simplification of nested radical expressions. In general, nested radicals cannot be reduced.